Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Speaker this morning will be Steve White. He's a software architect in the Microsoft Healthcare Solutions Group. So,
thanks. Oh my God. Woo. Sneak preview. Hi, Steve White. I'm not going to be talking so much about the algorithm side or the use case side. Dr. Haynor and Khan are both eminently qualified to be doing that. The angle I'm going to be bringing to this same general topic is how it impacts how we implement these, and for the computer science guys in the crowd, the interesting problems that I think it raises and challenges to all of us. So one of the big topics about medical imaging is not so much about the algorithms, but the data. These medical images that we're dealing with range from a few megabytes in size to gigabytes in size. Other kinds of scientific data, of course, genomic data, also share this phenomenon of being what I call too big to move. And one of the aspects that you want to handle with this is what I call playing it where it lies. So wherever you acquire the data, that's where you'd like to process it. And if possible, you leave it there. So what you want is to create for people this concept of a virtual presence, that the data is where you are, but in fact, it's left where it was acquired. So in fact, what we approach it with, and a lot of people approach it with, is a three-tier approach. We process the data where it lies and keep it there in a pre-processing, a middle tier, and a client-side environment. The pre-processing side is for static analysis. Organ labeling would be an example of one. You take the data in, you process it, you label it, you stick the data in the database. That data is much lighter, so it can be acquired at any time on demand. A middle tier analysis allows you to do interactive work. So you pre-process the data as much as you can, but when people start working with that data, you need to have an interactive tier at the server environment to actually process the data. But it's for the data that you can't actually move to the client. And then on the client side, as all web architects know, that's where you try and do all of your processing if you can, because that's where it scales. Because every new user brings with him or her new computing power. So this is what our architecture looks like. You can kind of ignore the acronyms, but basically from bottom to top is the ingestion side, the first tier, stored in the database, then the middle tier, which is right here, and then the client side. We also split it horizontally so that when you have multiple sites, as you often have in a medical environment, you have multiple acquisition sites, but you want to create a unified view of the data. You actually create what we call the modality sites, where the data is acquired and processed, which is down here on the left is where the data is acquired. But then when you send the data to a central site, the metadata to a central site, you can do relational queries and other computationally powerful operations on that data. The modality site also is where the images are rendered. So if you're going to be interacting with the data, rotating it, panning it, zooming it, window leveling it, which contrast or brightness, you want to do that on the middle tier because the user is now interacting with it. And on the client side, you have the, in our case, very computationally powerful clients that share their workload with the server to actually render the data. Oops, sorry. So that's the challenge of big data in terms of things like rendering and other basic kinds of processing. But another big challenge that's been alluded to in the entire presentation today is around it's what we call opacity, which is that it's pixels, it's voxels, it's image data. It itself does not have intelligence. You can't do intelligent queries on the medical data itself. So they're hard to find by themselves. That's why DICOM has a lot of medical header data. So you can use the DICOM header to get intelligence out of it. They're hard to navigate. As Khan was showing, if you can go through 1,000 slice series and get to the heart right away, for a clinician, that's a huge advantage. And they're hard to compare. As Dr. Haynor will be talking about, there's a lot of advantage to being able to do rapid registrations geographically. So there's a lot of advantage in use cases to getting this kind of semantic data. And what we've done is we've actually teamed up with a number of researchers to do this in a broader context of scientific data, medical data, of combining all this data into the larger semantic web. So again, I just want to recapitulate some of these ways that you can analyze this data. And you've seen a lot of pictures like on here where you have very dense labelings. Either every voxel in a 3D volume is labeled, and that would be one form of labeling, and kind of clustering analysis is very good at doing that, but it's a very dense representation. You have as much data in the segmentation as you have in the original data itself. Another one is a segmentation of 2D surface, where you're actually defining organ surfaces, for instance. Those can be compact, and you can represent them in a more agile manner, but they're still very complicated to compute and have their own uses. One of the things we've been focusing instead on, although we're focusing on all these areas, and we have some really great research from Cambridge in all these areas, from the use cases I'm going to be talking about, are really around very simple mathematical models so that these can be very compactly represented and used in very powerful ways, surprisingly. And as was mentioned in one of the questions, they're also extremely robust. So these very compact, simple representations are most powerful. And the one on the bottom is the one I'm going to be talking about, these bounding box representations. So you've heard about these, and you guys all know these notions of regression forests or decision forests for doing clustering and that kind of analysis. What we're doing is what are called regression forests. And what they do is they actually predict each of the 6 surfaces of a box around a given organ. So what we do is we have experts go out and label images with bounding boxes. In fact, we do full segmentations of these organs, but then we define boxes around the organs, bounding boxes. And what we do is to take hundreds of those and train a regression forest on that. Again, the regression forest role is to take a forest of trees, each node of which is predicting the location of those 6 surfaces independently. And so its goal then is just simply to take the input of a grayscale 3D image and produce a series of 6 estimates, a series of 6 bounding boxes to locate the organs. Obviously, from a storage standpoint, 6 coordinates of a bounding box are pretty easy to store. And so you end up with a very compact representation. The use cases around that are kind of specialized. So decision forests do categorization and produce these dense models. These regression forests are focused on localization and sparse compact models. And the research team, as you've heard a couple times now, led by Antonio Cremonesi in Cambridge, Microsoft Cambridge Research Laboratories, has really pioneered this work. So the use cases are you've heard before and you'll hear again, are around navigation. I think Khan did a really great demo of how a clinician can go through and quickly get to the heart or the thorax or whatever. Registration, as Dr. Haynor will be discussing, is a particularly powerful use case. But it's an interesting one from an architectural standpoint, and that's kind of the direction I'm going to be going, which is to say these very sparse representations are very portable, so you can move them around the web. You can do queries on them, and you can not only find images that have a thorax in them in both cases, you can find the thorax, the historical thorax case of this set of patients that present with the same symptoms. You can get just those segments of the images, so you have a vastly more compact and therefore high-speed response from the network on getting that data to you. You can pre-register them, and then you can do your fine-scale registration locally on your host machine. But it also, well, let me just finish. Report linking. Khan showed you a very powerful concept, which is to have your radiology reports hyperlinked to the data, so you can extend that model, and then search, as Khan showed you. So in this concept, then, we have to go back to the original model, which I discussed with you, which is how do you actually architect this? And when we started out this project, the labeling software, which you saw, ran in about a minute. And so in that case, what you say, that's an ingestion tier. You take the data, you label it, you put that data in the database, that's it. What we're now seeing is that you can do it in real time. So we've moved that code to the middle tier. So now it can be done interactively. So you can take any data set anywhere, label it, and run it, and do the analysis in real time, or near real time. I've already talked to you about the registration code, which does a good job. But another very interesting aspect of this is the registration by using this hierarchical approach, where you use the coarse organ labels as a pre-registration, pre-filter and pre-registration, not only speeds things up, but vastly actually improves the reliability of the registration. The picture on the left basically shows you global minima, whereas if you use other techniques that are well known, there are many local minima. So you actually end up with a much higher success rate in your overall registration by using this pre-stage registration. So this is a recurring theme. If you go through and look at the literature, as most of you have, you'll find that almost all of these algorithms that people propose are hierarchical. There's a core stage to a fine stage kind of registration model. And this is what we're proposing as one example of an excellent first stage for the processing. Which brings me to my conclusion, really, which is that all of these algorithms require multi-stage analysis. One area that I've been working with colleagues around the country is in my favorite topic is to label brain regions. There are multiple kinds of algorithms that operate very well in labeling cortical structures. We believe that Antonio's algorithm would do an excellent job in labeling subcortical structures. Very stable, very rigid, very easy, amenable to this process using MR data. There are other groups, for instance, at Johns Hopkins, that are excellent at labeling white matter, DTI-based data. But they require priors. They are much more robust if you actually give the algorithm subcortical labels ahead of time. And then there are other algorithms that are really good at labeling cortical structures. Now, this is particularly challenging, neocortical areas. They're particularly challenging because the cortex is this big sheet, and there are a lot of theories about where functionality and organs, functional areas can be mapped on that. But clearly, or we believe, if you had a very hierarchical and robust labeling system underlying those algorithms, that you could actually achieve significantly higher, better results in registration of even cortical regions, even with plasticity. So this is just one example. Registration could be viewed as another example of this, where you use coarse registration at the first level and then hierarchical, finer registration algorithms above that. So what we're working on, and what I'm working on, is an open architecture where people can actually plug in their algorithms, make use of the metadata produced by prior algorithms, including our own. And finally, not only that, but the biggest problem goes back to my original point. You have to play the data where it lies. So all of these algorithms rely on having the image data available to them and the metadata available to them. So they have to actually run back at where that modality, in our case, medical image modality, is. And so this kind of presents what I call the inverse JavaScript problem. You really want to be able to create a situation where the client at the top of that stack can say, I want to run my analysis. I'm going to send my script to the source modality site, run my analysis using both the metadata we and others have produced, either in real time or on a stored cache basis, and then produce my results, hopefully adding to the metadata wealth in the process. So this is an open question. I've been working with colleagues at MIT and other places to try and think of ways we could do this collaboratively. Clearly, if any one group tries to do it in an exclusive way, that would just defeat the whole purpose. So this is one of these data net problems that we've been pursuing, and would love to talk to anyone interested. And that's it. Are there any questions?
Thanks, Steve. Is there any questions? All right. Our next speaker this morning is David Haynor, Dr. David Haynor, and he is a professor of radiology at the University of Washington. So, Dr. Haynor.
Thanks, Rick. Let's see. Okay, so I'm going to give you a view from the trenches, okay? The consumers of the sort of things that Steve and Con were just describing. Thanks, Microsoft. Okay, hopefully this will work. Okay, good. So what I'm going to do is go over a little bit of the things that have already been discussed. This will be an interesting opportunity for you, since all these talks were done independently, to see how much convergence and divergence there is. Actually, Steve had explained to me what semantic tagging was, but once I understood it, then I said, oh, okay, now I know what you're talking about. All right, so what I'm going to do is talk about some of the aspects of semantic tagging in the clinical context, and just an example of some of the things that you can do with it. Okay, so what I want to do is start from the clinician's perspective. And the thing is, we're not hurting for information. We're not hurting for knowledge. By many metrics, the amount of information that's now available on even the most minute subject in medicine greatly exceeds the capacity of any caregiver to understand it. And here you can see this is the rate of new article additions to PubMed, the published literature. So it's rising linearly with time. The amount of total amount of information, we'll say, is quadratic at worst in time. Here's an article on one gene, just one gene, and remember you have about 25,000 of them floating around your body. You notice that at the 5 years ago, there was a little bit of a lull, and there were only 4,000 articles a year appearing on P53. Since then, that's been going up a little bit. This is a very important gene. 30% of the people in this room will be dealing with cancer at some point in their lives, and dysregulation of this particular gene is thought to be important. But you can imagine the oncologist who wants to understand the literature, the problem that he's facing. Here's a drug that is now in use that just came out about 2 or 3 years ago in clinical use, and has been was in lab investigations for about 8 or 10 years. And you can see, again, the same trend. So first point is that information is growing really rapidly in medicine. The rates of accrual, even on very specialized topics, exceed the practitioner's capacity to learn. At the same time, there's, of course, a lot of discussion in literature about the rising cost of healthcare. What that translates to for us is a drive to increase productivity. Now, typically, we're looking at about 10 to 15,000 images in a day's work, any one of which could contain information that's important to a patient. What I'm trying to convince you of is that physicians, radiologists in particular, like me or like Khan, are pretty much at our limit as what we can do. So the first conclusion is that any new information is fine, but radiologists, medical school spends a lot of time giving you the idea that you want to do the perfect job. Okay? When you go out into practice, you discover that really the challenge is trying to do a pretty good job, and it gets a little bit harder. Every year. So there's a consequence, which is that if you want to present new information to practitioners, it has to come with a near zero cost in terms of additional time. We already think we're doing a pretty good job. If you provide us with information that we can extract, but that takes an extra 5 or 10 minutes a day, we're probably not interested, because there's lots of stuff like that we could be doing. So consequently, the added labor cost of a new information source is a very important consideration in technology. So let me just remind you a little bit about CT, because it'll be relevant to what we're talking about. It measures electron density. A standard size American, of which, of course, there are fewer and fewer every year, is somewhere between 50 and 100 million cubic millimeters. And a cubic millimeter is around the size of a pixel. So that gives you a rough idea of how many pixels are in a typical CT data set. Now, on the basis of density alone, we can easily distinguish about 5 or so classifications of tissue: air, fat, soft tissue, calcification, and bone structures, and foreign bodies. And the rest has to be understood currently by humans in reference to knowledge about human anatomy. And just to put it in perspective, one of the hospitals I work at, Harborview, has about 400 beds, so it's a medium-sized hospital. It does about 200 CT scans every day, of which about 120 are body-type scans. So in trying to understand where semantic tagging, and I'll explain to you momentarily what that is, let's think about human variability. Well, we're all used to the notion that different people look different, and we're also used to the idea that most of us are quantitative variations on a theme, or on maybe one of a finite number of discrete themes. We know that things like age, gender, color of hair and skin, lighting, and the presence of foreign bodies, like these glasses here, all have some influence. But nonetheless, we can all recognize faces in scenes, and we know that this is so this gives you an idea. This is 2D human variability. Now, how does that translate in 3D? Sadly, we don't, or perhaps it's a good thing, we don't walk around with X-ray eyes, but after you have looked at many scans, you start to get an appreciation for how it works, and it's much the same. That is to say, there are quantitative variations in things, but basically the eyes are always above the nose, and in the same way, for example, the liver's generally below the diaphragm. Now, a question was asked, well, what about anatomic variance? Turns out for most of our diagnostic things, they're a relatively small fraction of the total, and they're easily recognized as anomalies. But there's some consequences of that we'll come back to. So what are the parameters that determine what the world would look like if you were a mobile CT scanner? Well, age is one thing. The amount of fat versus muscle is a huge thing. Basically, organs have shapes, and how do you pack these irregular shapes into a body? Turns out fat is used to fill in all the interstices. So we're all, as you'll see in a moment, solid organs floating in a sea of fat. Obviously, gender has some influence, but in general, for 90% of the body, you would be hard put to, it's much easier to come up with a good estimate of patient's age than it is to come up with an estimate of knowing what gender they are, unless you happen to be looking in the pelvic area. The administration of contrast is sort of a radiologic artifact, but has a big influence on the appearance of images. And then, of course, what we're really interested in are the effects of disease. These are organ enlargement, shrinkage, texture change, local changes, the effects of treatment, and then skeletal deformity, which of the deformities is probably by far the most common. Okay, so again, just to give you a rough idea, and then I'm going to show you a movie from the MSR group in Cambridge. These were 3 CT scans that I got from Harborview, and I did the best job I could of coming up with the same, with essentially the same axial level, that's from top to bottom, for all 3 patients. These are 3 women, and you can see they're built on very different plans. First of all, you can see that, again, as I said, we're all built of solid organs floating in a sea of fat. But you can see that the amount of fat differs quite a bit. Although the general plan is the same, exactly what's apparent at a given level is a little bit different. For example, only in this patient does the right kidney show up, and again, up in the chest, you can see again their quantitative differences. Okay, now let me just. This is just a movie that'll give you a visual on how on human variability. So we're looking at the same thing, just a bunch of people, and this gives you some idea of what the level of variability. And as you can see, it's very similar, sort of in 3D, to what we saw in 2D. Okay, so what is semantic tagging? Well, at the end point, as Steve was saying, it's a detailed organ labeling. You label essentially every voxel potentially in the body according to its name, according to a standardized set of names. Now, historically, within the image processing community, the approach has been very much this hierarchical approach. And typically, so there's been a lot of emphasis on the local problem of determining the exact boundaries in 3 dimensions of an organ. Once a human has told the computer approximately where the organ is, so you can distinguish between delineation and recognition. Okay, and those of you who are in computer vision know that recognition is often the harder problem, because it requires some domain knowledge. So really, within the last few years, there's been increasing interest in this problem of eliminating the manual initialization steps, which would allow potentially complete automation of organ labeling. It's what I'm going to call rough localization. And of course, in the clinical context, it's important when you're done to produce some visual feedback as to what the computer actually thought were the boundaries, because sometimes it's going to make mistakes, just like humans make mistakes all the time. in this area. So visual feedback is essential. The computer in this is acting as an assistant. It's not acting as another physician. So this was just sort of a recent review of the literature, and what you can see actually is that most of the articles on the subject are pretty recent. And here are some of the organs that people have looked at: the heart, the great vessels, prostate, rectum, liver, esophagus. And now I'm going to talk in a little bit more detail about what the people in MSR have done. And as Steve explained to you, the goal here is to localize a bounding box. Now, one thing that's interesting is this is done independent, and as Steve also pointed out to you, it's done, well, we'll talk a little bit more about how random forests are trained, but basically what they're trying to do is predict the offset of each organ from every voxel in the body. And then you take a vote of the most confident voxels, and you get an estimate, essentially, of the offset, those six n parameters, if n is the number of organs you're trying to identify. One interesting thing is this works pretty well independent of the size of the individual, which seems a little surprising. We know the distance between the heart and the liver is quite different if you're 3 months old versus 30 years old. And so it works pretty well without normalization, but this is an obvious sort of improvement that could be made. The idea is to compute many, many image features at multiple scales for every single voxel. You train multiple trees to predict the offsets of the organs from the current voxel, and then an ensemble prediction using the highest confidence voxels is done. Mean error is on the order of a couple of centimeters. Now, as is usual in this case, the training is slow. The forward computation can happen in a few seconds. One of the interesting things about this, one of the things I like about this method is, first of all, it's very generic. The machine learns all the features. And a second feature that I think is important is that the training, which is the time-consuming step, is completely parallelizable, because basically you're training an ensemble of trees, and so if you have 10 computers, you can train 10 times as many trees, or train trees in a tenth the time. We've also starting to work now on generalizations to the spine. It's one thing to find the liver, which is a giant hunk of meat weighing about 10 pounds in the right upper quadrant. Not too hard for a child radiologist to find. But it's much more difficult to localize the skeletal structures. They're all high-density structures. They have a somewhat unpredictable, as we move around, relationship to one another. And it's important to be able to label, for example, individual vertebrae correctly, not just say this is part of the spine, but rather to say this is the 9th thoracic vertebrae or the 5th lumbar vertebrae. To do that, you have to do a little more constraining. You have to look at multiple predictions, basically jointly, rather than singly. And currently, we're doing that with a Markov process. So, as I mentioned, the step from rough localization to semantic tagging actually builds on what the image processing community has been working on for the last 20 years in medical imaging specifically. And once you have a rough idea of where an organ is, we have many, many methods for refining that estimate. This just reminds me of the usual thing, that as you try to use human input more and more while retaining the same level of performance, the amount of software cleverness that's required goes up. Okay, so clinical requirements that we've identified so far, essentially 0 user time. Okay, this doesn't mean 0 computer time. It means that the perceived time by the user has to be 0 or near 0. And by near 0, what I mean is a second or two. Okay, a minute. That can be how long we spend. If we spend 5 minutes with a study, or 1 minute if it's a routine simple study, we're obviously not willing to let an algorithm run for a minute or even 30 seconds. So we're down in the few seconds range. We certainly have to display the results just to make sure that situs inversus wasn't incorrectly identified. The other advantage, of course, of displaying the results is that the system can get smarter as time goes on. What wasn't emphasized was that the performance of these systems, besides being limited to some extent by the model, is also improves with the more instances you have, the more training that you have. But the training, producing the training set, having somebody carefully mark all the images, is time consuming. So there's the possibility, if the user can look at the results and say, yeah, that's a good job, that was a bad job, that the system can get smarter as time goes on. It's been trained on a few hundred images. We see 100 images a day. If we grade the results A, B, C, D, E, in a week, we'll have many more training sets than we originally started with. Okay, so now I've talked about semantic tagging, and the way I think about it is that right now, as Steve mentioned, these image data sets are 100 megapixels of essentially unintelligible numbers that really require a human to make any sense of it. In order to fit imaging data into a reasonable informatics system where we can do reasoning, or we can do correlation, or we can do recall, or any of the kinds of things that we would like to be able to do in order to leverage the immense amount of data that we're requiring, we have to somehow turn that big blob of data into a parsable data container with identifiable components. It's sort of like natural language processing and free text, but as I hope I've convinced you, it's a somewhat easier problem. We are all built on the same plan, more or less, so it's not like there are a billion ways to say something. There are only a few qualitative variations on anatomy that are relevant in any situation. So just to give you an example of the kinds of things that you can do with this, I'm going to describe four possible end user applications. One is a deformable atlas of human anatomy for the radiologist. One is talking about detecting changes over time, and sort of with basically detecting changes over time. A third is about osteoporosis. Did you all drink your milk this morning? I'm sure you did. And then the last one is about using the image data, just like when you go in, you get blood tests and serum sodium, creatinine, and so on. There's plenty of quantitative information that's available for free, essentially, in the imaging data, but currently we can't collect it because radiologists are well aware of it, but it's too expensive for us to collect that data, and we don't have any reproducible, bias-free, low variance way of collecting that kind of information. Okay, so let's start with the first, deformable atlas of human anatomy. So think about it. Semantic tagging followed by, we'll say, pretty good organ segmentation. Doesn't necessarily, even in this context, have to be absolutely perfect down to the pixel. Can give you a local affine map between portions of an image set and what is essentially an atlas, a universal human who can be stretched locally, sort of like Gumby, can be stretched locally in various directions. So the anatomy corresponds basically one-to-one with the image set that you're looking at. These locally affine maps, they're initialized by that rough localization, and then by organ segmentation, and then by matching it to an atlas. Again, this kind of processing, A, can be done entirely offline to the extent that rough localization is fairly reliable. Again, it doesn't have to be perfect, just has to give you a pretty good guess to start with. And then the details will emerge from the local registration. That can be stitched together to make sort of a global polyaffine map. And then, just as Steve was saying, that's a lightweight structure that can be saved and just appended to the data. Once you've done that, annotated images from the atlas can be used to automatically annotate the patient's image. So here's an example of the kinds of things that we were looking at. On the these happen to be MR examples. These are two different patients with leg weakness. This is a 9-year-old girl who developed weakness following hernia repair. And if you look at the two legs, the left leg, this is the way radiologists talk. This is the left leg, not, as you might think, the right leg. The left leg, you notice that the muscles in the front, and this is the front of the patient, the back of the patient, the outside of the patient, the middle of the patient. You can see that the muscles in the front of the left leg are higher in intensity than on the normal right leg, and in addition, they're quite a bit smaller. And if you look at the atrophy, you'll notice that it's all in this anterior compartment. The posterior compartments are basically the same. Okay, so this is a good example. This was a femoral nerve injury. There's one nerve that innervates all these muscles, and it was injured in the course of her hernia, in the course of her hernia repair. So this is a pattern recognition kind of thing, which is easy to do now that I've walked you through it. But they're much more obscure patterns that are going to be a lot less familiar to radiologists. Here's one that's a little more obscure. This is a woman with ovarian cancer who developed some weakness in her left leg. And if you look, you can see these muscles that are labeled 1, 2, and 3 are actually smaller than their counterparts on the opposite side, and also again higher in intensity. Here's an axial image, same woman, some of the same muscles. So the questions, this is just a toy example, but the questions that arise are, where are we in the body? What muscles? What are the names of the muscles that have been affected? And how can we use the knowledge about which nerves innervate which muscles to answer the question of which nerve innervates them all? Sounds like something from the Lord of the Rings. But so imagine that we'd done this sort of rough localization followed by semantic tagging. And you could imagine now that here is a scan, a CT scan now, that we're looking at, and here's an atlas image, and I picked them to be corresponding. And you can imagine, you notice that first of all, they don't match perfectly. Okay, again, the patient that we're looking at here is supersized relative to the patient over here. But if you look in detail, you can see that the organization of the tissues is exactly the same. You can imagine that you're cruising through this image. You could have a linked cursor over here that was telling you where you were in this fully annotated image. Okay, so we spend the time to produce one atlas. We do the rough localization. We now have this linked browsing, and all of a sudden the radiologist or whoever's looking at the images has access to everything that's known about this particular muscle. There's no reason why we have to limit it to what nerves innervated. How about the blood vessels that are relevant? How about diseases that preferentially affect one group of muscles over another set of muscles? These are the kinds of questions that we have to deal with, and currently search is essentially search is manual and tedious. Okay, so registration. At any academic medical center, you spend a lot of time looking for changes in a patient over time, whether it's cancer, whether it's multiple sclerosis, whether it's progression of heart disease. Diagnosis is easy. That's sort of a binary, discrete decision. You do or do not have prostate cancer. Looking at individual lesions, is the disease progressing or is it improving? That's very tedious, okay? And I'm going to show you some multiple sclerosis images, and you'll get an idea of the problem. So if we want to do, there are tools that let you do manual initialization. They don't currently fit well into the PACS environment, which in our case, the University of Washington, is essentially a closed environment. And moreover, there's some manual initialization that's required, and then a lot of computation. So the zero cost rule applies, so we don't do it. We do our best for eyeball comparisons. Here's an example of the kind of thing that you might be able to do. This is a 57-year-old woman with multiple sclerosis. This is what she looks like in 2011. This is what she looks like in 2007. Now, these black areas in the middle are the ventricles. They contain spinal fluid. They're in the middle of the brain. So basically, you want your ventricles to be as small as possible because you want your brain to be filling your skull. What you can see in this woman over a 4-year period, the ventricles have gotten bigger because the multiple sclerosis caused some actual loss of tissue. In addition, you can see new lesions have appeared. These are the kinds of comparisons that we have to make visually. And typically, there are about 100 of these images that we have to scroll through. And you can imagine that we'll look at all these lesions, or at least enough of them to get an idea of whether we can say lesions are the same, they're much worse, or occasionally a few of the lesions have disappeared. We also look at volume loss. We'd love to have automated tools for doing it. And so I think the point that Steve was making is that rough initialization can facilitate image comparison. Again, registration can be done offline from the user perspective. Before the images are viewed, we can use a link cursor, image warping, whatever your favorite tool for comparing images. If we get a really good registration, which is typically only possible in the head, which behaves essentially as a rigid body, we can even use subtraction to highlight areas of change. Okay, now let's talk about osteoporosis. It's a big health problem. There are about 1.5 million vertebral fractures per year. It's basically due to the loss of bone substance over time. It's a big problem in elderly people. If any of you are taking care of a parent, like I am, with a hip fracture, for example, you can appreciate it. It's preventable to some extent through diet, exercise, quitting smoking. It's treatable, fall prevention, medication. It's underdiagnosed, and screening is tough, and it's frequently missed by radiologists. Here's an example that was actually missed. This is a 66-year-old woman. She fell. She broke this particular vertebral body. I measured the density here of 2 of her vertebral bodies. This one in red, it was 100 in Potrezibes. Hounsfield units is what CT. So 100 is kind of the lower limit of normal. So she's at the lower limit of normal in this vertebra and well below it in her lumbar vertebra. 4 months later, her back has been hurting her. She has not been very active. She's been in bed. What's happened? The density of this vertebra hasn't changed. The density of this vertebra has decreased now from 81, which was, as I said, already below normal with 100 being sort of a cutoff. And now this places her at enormous risk for additional fractures and might be an incentive for a physician to mobilize her a little more vigorously and get her to drink her milk. Now, this information has to be manually extracted. I did this because this happens to be something that I'm interested in. But you can imagine how much better life would be if we got a report every time we did a CT scan. Here are the density by vertebra. Here's the aggregate density, the average, thoracic, lumbar spine. And here's what it was the last time the patient had a CT scan. Okay, so the goal then would be to identify patients with low bone density, understand the effects of treatment. Again, this is information that we're collecting for free. It's in the blob, but we need computer algorithms basically to extract it. Okay, so on the same theme, there are other quantitative metrics that we can think about. Density or texture, and I just happened to, I listed a few. We can detect fatty liver, cirrhosis. We can detect osteoporosis. You saw cataracts in the lens. We can look at the health of portions of the lungs in people with emphysema. Probably most important from a public health point of view, we can get an idea of atherosclerosis just because calcification is one of the endpoints of atherosclerosis. Your vessels become calcified by basically, if we could identify the vessels and come up with a calcification metric. This has already been validated, by the way, in coronary arteries, but again, very tedious, requires a specialized application, can't be speeded up offline. Okay, and then size is also a big thing, obviously for following tumors, but even for looking at organs. Your heart shouldn't get too big, the wall shouldn't get too thick. Your lung should be about the right size, not too big, not too small. We don't want the liver to shrink. We are interested in why it might be expanding, maybe because you're drinking too much. Kidney size probably is a good marker for early kidney failure, maybe even before it's detectable with blood tests. Okay, so this gives you some of the things that might be possible with this paradigm that Steve described, where most of the recognition is performed offline, where various lightweight pieces of information are gathered and stored with the images. I think, and while still respecting that zero cost rule, you know, I personally think it's pretty exciting. There's a lot more work to be done. I mentioned normalization. Maybe we need different random forests for different sizes for different types of patients. We can increase the numbers just by learning as we go. If we put this into a clinical application, we can obviously extend it to other body parts. We need to do more validation on image sets that have significant pathology. We have to figure out how to describe these lightweight structures in a portable kind of way. And you know, then ultimately the final thing is to show that it's clinically useful. So in conclusion, semantic tagging is the last mile as far as I'm concerned in medical image segmentation. We've made a lot of progress in the last few years. And when you can parse medical image sets, you get access to a rich variety of information that's essentially there, that's already there for free, but that currently we can't afford to extract. I just want to acknowledge some of the people at Microsoft I've worked with. Thank you. Questions? Yeah.
Can you read the run it over there?
Thinking even now about upward compatibility.
What do you mean by upward compatibility?
If you're trying to track a patient for 25 years, you should be thinking about making your semantic tagging in your atlases, or maybe having some kind of standardized file format, or some extensibility to the tags, so 25 years from now you could still use that base data.
So the question, and I'm just repeating it for the benefit of posterity here, the question was how can we represent this information in a portable, universal format that's documented and that can evolve over time. And so all I can say about that is that it's definitely a problem. It's clearly a solvable problem, but I think as these I think the availability of this kind of information is going to raise the priority of the task that you just mentioned to a level where people will be happy to work on it.
David, can I respond to some of that stuff? So there is existing efforts on terminology standardization, effort called RADLEX by RSNA, which is Radiology Society of North America, and defining tags and anatomic structures and standard terminology for it. And that's what we are using, how we represent our data internally in our databases. And RADLEX is part of our national standard by National Library of Medicine on how to create standard terminologies, part of UMLS and SNOMED CT coding scheme. So there is effort in the medical industry to do that stuff, and we are using those standard terminologies to represent the data.
But extensions will be
correct.
Will certainly be necessary.
Thank you. That was a very interesting presentation. When you talked about segmentation, that was mostly cross modalities within a patient. Is there any work on trying to map these images to a common reference space model that would be across a group of patients?
So the question was whether images can be mapped to a common reference space. And so, first of all, the naive answer to that is, well, of course. I mean, it's us, right? I mean, there's our physical reality. So there must be some way of doing that. The so there are two ways to put it. Cross-modality registration within a given patient. I have an MR, I have a CT scan. That's a relatively well-solved problem. The parametric space of registrations that you need is relatively small. For example, in the head, just rigid body registrations are sufficient. And so mutual information is a very successful metric for doing that. In terms of mapping everybody into a common space, essentially that would overlap with the idea that I talked about the deformable atlas. I mean, to the extent that you have a deformable atlas, you have mapped everybody into an approximately common space. Now, characterizing qualitative variations as opposed to quantitative variations in that space is a little bit more tricky. I mean, people who have only one kidney, let's say, well, what happens to their right kidney if it doesn't exist, or have a horseshoe kidney or a heart that's the wrong way? So there are some minor problems, but fundamentally, both cross-modality registration within a given patient, and I think in mapping people to atlases is feasible.
Yeah, my question is that it seems that the method is heavily biased towards the modality like you are doing on CT and MRI scan. Now, if there are other modalities like say echocardiogram or ultrasonogram, where actually you have more difficult problem of registering because you do not have really the reference points.
Good
so
question.
Will this thing work?
Good question. So I dealt with these two modalities, MR and CT, because they are the only, for all practical purposes, they are the only 3D modalities, okay? Now there's a whole culture out there of what's called 2D, 3D registration, which is very important, for example, for image-guided surgery. When you're doing image guidance, for example, you typically are using X-ray or ultrasound, basically 2D modalities, and you might have a preoperative study, which is a 3D study. So you have a study. You have a single 2D image that you want to orient with respect to a 3D data set. So people are, and there are lots of approaches to that which are pretty successful. One of the problems with annotating 2D images, some types of 2D images, is that they contain a lot less information than a 3D image. Just to give you an example, if you were to show the best radiologists in the world one CT slice and say, what vertebra are we looking at? Are we looking at first lumbar or second lumbar vertebra? They would be able to do slightly better, somewhat better than chance, but certainly not perfectly. So when you're doing 2D, 3D registration, there are a whole set of new problems, but again, it is a clinically important one and one that people are working on. But it's harder. I mean, like if you look at a random ultrasound image, you don't happen to be told exactly what you're looking at. It can be pretty darn difficult to figure out where you are. Whereas if you look at a CT scan, you can always tell where you are.
I just want to make one more comment on that. I mean, our focus has been, and as David talked about, is really what can we do to make this more generalizable and used by a lot of different people. So the idea of here there's information already exists in scans. Can this semantic tagging methodology and how we recognizing structures surface that information automatically? So that data is already there today in every single scan. It's just that we're not making an effort to surface it to the clinicians, or they have to make an extra effort to go do something like that. In a 2D space, it becomes a very specialized use case where somebody has to actually do the acquisition for whatever reason it is, and mostly becomes a surgical planning or as image-guided procedure point of view where the registration needs come into play, not for, data is already there, can we surface more data by understanding what organs or what structures are in there. So the reason we as Microsoft have not tackled the problem is because we think it's a very specialized use case. It's not that idea of information discovery type of use case right now, so that's why we focus mostly on the 3D data set type of data.
Thanks very much, and thanks to all our speakers, Dr. Siddiqui and Steve White and Dr. Haynor. So thank you all for attending today.